My name is Jin Sang, and that's my colleague Hao Dong. Yeah, today our topic is beyond the blacklist. We talk about detection malicious URL using machine learning. And we have a full contribution for this topic, Hao and myself, and also David and Chenhuai. And David Chenhuai didn't come today. All us is from the Houston network. We are from the Silicon Valley office. Yeah, that's a brief introduction for all four. And firstly, I will give the simple introduction and the problem overview, and then we will talk about the topic, the malicious HTTP traffic detection method, and then we go the machine learning technologies we use, and then give some result and our data. And finally, we will have a short discussion about beyond the malicious URL, the ways we use, we did, and finally is the conclusion. So, firstly, I think that maybe not many people know our company, Houston Networks. I will use one simple sentence to describe the Houston. Houston in last year, 2016, where is recommended by NSLab NGFW test with best value. Yes, so you can check website. But today we will not talk about the NG firewall. The work we taught today is we did in past years, and yeah. And actually, this morning the keynotes and the speech I'm very exciting. Also agree a lot because for me, I also in this network security defense industry almost 16 years, and I fully agree the security is a journey. Yeah. So if we see the network defense side, we see in about 20 years ago we talked about the firewall, and then Fortinet proposed the UTM, then Palo make the NG firewall, and then, for example, FireEye proposed the sandbox technology, and in the last 3 or 4 years, we heard a lot of word about maybe the big data, threat, intelligence, machine learning, deep learning from last year. Yeah, so I think, yeah, for me, right, part 3 is the major the milestone, and right now, I group all the technology as one word, intelligent. And from our view, the intelligent technology from algorithm, maybe just as data analysis, machine learning, cloud computing, and behavior analysis. But for model, right, is kind of same thing. So you need to define the object, and you also define the feature set, and you need your own customized model and calculation and get a model. Because we are not doing research, we also do the product. So from product view, we have a lot of experience. From our view, I think the false positive and then false negative is the key things we need to concern about. Also, like just the keynote said, visibility. And from our view, you need to provide fully forensic visibility. And finally, because we talk about something like firewall, something in the inline device, also need to provide fully the mitigation, yeah, some stuff. Okay, and then the detail for ourselves, for the overall, we think the technology, we think, so we call the NG firewall. I mean intelligent. That means we only not study and use the intelligent machine learning. Also, we combine together with the NG firewall technology. And for deployment, I think everybody maybe heard about the way not only currently the defense, not only in the perimeter, also we need to defend in depth for the inside network. From the overall architecture, I also think that this morning the people already talk about. So the overall, I think not only we use you need to use new technology to detect the suspicious event. For example, DGA, malicious URL. Also, you need a new architecture and technology is multi-layer, so you need to do fully code revision. So the purpose is to input use false negative and positive. So, but that's overall. But today we are not talk about all these things. Today we are focused on one of key things. So we did this year is we use the machine learning to detect the malicious and unknown URL. So let's now I pass to the how. Yeah, he will continue to give the detail. Yeah.
Okay, thanks, Jim. I'll give you an excellent introduction. So for the next 30 to 40 minutes, I'm going to talk about in details how are we using machine learning technology to try to figure out how to address the issues that are how to detect malicious URL within your network. So, in your network, some hosts can be compromised, and when they do the malicious activities, they normally make a connection to the outside. So we think that's the problem we want to address is to figure out what's the effective way to detect those connections. So in this slide, I also put a diagram of this cyber kill chains. It's defined have 7 phase of intrusions. Okay, the 7 is kind of like a magic number here. So we talk in the keynote talking about 7 axioms. So our traditional defense technology try to protect your parameters. So they want to defend the attacker outside. But we began to realize this is not working. Actually, there's more than the technical way to enter for attacker to enter your network. So the best strategy is to think within your network is not safe. So we have to shift the focus from the parameter defense to the post-breach defense. So in this diagram, we think we are for better defense, we need to focus on the number 6 and number 7 stage to detect. So before the damage is done. Okay. So next slide we show how do we do the post-breach detections. Our traditional way is using a signature-based. So this is we probably everybody knows the limitation of that. So first, there's a greater number of malware every day. So it's almost impossible to have this malicious URL as a signature based blacklist. The second are to keep up with malware changes. It's really hard to maintain, to update this blacklist. And third, it's simply not cool. So, we want to have a new technology. So, as in this keynote, so everybody knows these days add machine learning to add a defense mechanism. So, it's true that our machine learning can somehow, everybody uses that, but for us, it's not just a research, it's a project. For us, it's also a product. So in this talk, I'm not simply talking about the strategy. We're also talking about some kind of multi-dimensional ways we try to make the product. Okay, in this slide, I quote a kind of famous quote from Donald Rumsfeld, which was our former defense secretary of the United States. So basically, it's a very interesting to read. So we have no knowns, we have no unknowns and unknown unknowns. So the machine learning approach is try to, based on the existing the knowns, we try to know unknowns. Then we can defend the network from the proactive ways instead of reactive to what already happened. Okay, so then the question is what kind of method we try to use? As I already said, I think using the machine learning technology is kind of it's not very new. When we started the project 3 years ago, it's kind of new, but now we see the trend that everybody start to claim they have this kind of technology built in. So I'm going to talk a little bit about the way we use. So the topic of this talk is beyond blacklist. So we want to detect malicious URL. The URL is basically HTTP URLs. So HTTP is still most used protocols for the compromised host to make connections. The information we look at, we're based on just the URL itself. So we basically just look at the URL, the lexical features. So basically just words. We don't look at the content. So unlike some other companies, they actually are examining the content, what the file is downloaded, what's the page HTML and JavaScript embedded. So we look at only so this way is a much simple, a lightweight way. But it doesn't have its disadvantage. So we basically try to determine just based on the look. So we first to address one issue is very complex issue of URL strings, which is parameters. So as you can imagine, parameters is so dynamic. It could be anything. So the way, the approach we try to use is most focused on the other one. We try to catch a commonality between the malware connections and try to figure out a pattern that can be used for prediction. Okay, this slide shows a diagram of our overall system. So we have our malware PCAP, basically the network trace. We have a big repositories. From those data, we extract the HTTP requests. We convert those requests to some kind of feature vector in order to do the machine learning studies. So we use these request features. I'm going to talk about the method later to do the machine learning and create a model. So in the right side, those rectangle with its colored circles is kind of our models. We also have some other component which can do the post-processing to add more information to the models. In the bottom, you can see there's a periodic update. So we have this incoming thread information every week. So we constantly periodically update the models. Okay. Next, talking about the where we can deploy, where we can build. Basically, we can deploy as a parameter as integrated with a firewall appliance, and also we can do some kind of server-centric, some kind of inside your network. We can deploy close to your servers and do the protection around the server. So our model is built offline, but we can also do in the cloud and do the periodic update. And also we look at the information not just based on information incoming threats. We also look at the device feedback, and also we have this global correlations. We look at the geos. So some location might have a special kind of feature event happens that might cause a false positive. This slide is a diagram shows one way we deploy our detection models. So in the bottom, we show how we do the build. We have the batch and incremental training to build the model. We also take the feedback from device. So if system admin say, this is a false positive, so we can add this information as feedback to our training process. Okay. Since we are doing HTTP URL detections, so let's first take a look at what component of HTTP. So look at the URL, we can see there's host domain names, there's URL path. Basically, it's like on server, kind of like a file path. Then there's a question mark. So after that is the parameters. Parameters is look like just a key value thing separated by the end. So our detection module look at 5 components. So I think here we list 3 are part of the URL, but we also look at like HTTP headers, for example, user agents, which is also kind of low-hanging fruit. It's easy to use some known blacklist. So when we're talking about beyond blacklist, actually blacklist is still an effective way. It's just not adaptive enough for the changes. Okay, so our detection modules we have 5 modules. We look at each part of the URLs very carefully. We call it put the URL on the microscope. The first one is host domain name modules. I wish I could have more time talking about this. This is a full-blown machine learning modules, which using about 17 features like a TLD, registration, no registration, some kind of, it's also based on just the text. You look at some kind of 2 gram, 3 gram transition Markov model. So when we train with thousands or even millions of generated domain names, and also with millions common popular wide domains. So we can achieve very high accuracy to detect DJ created generated domains. If it's a little bit longer than seven characters, because shorter one is hard. It's really hard. User agent is simple, and the URL path will basically collect some kind of updated blacklist. So one case, like last year when the ransomware break out, we can take out some kind of blacklist from ransomware tracker website and put it into our signature blacklist. URL parameters is the topic of today. So if you look at that, our parameters basically is so dynamic, it could be anything. So how do we to extract features from it and start our learning process? Okay, before talking about just something I mentioned before, is we also look at called HTTP header patterns, which are also called like a browser fingerprint. The purpose of this is not for detection. It's basically to try to reduce false positive, because we found that malware tend to use less headers because they don't do things like cache control or do not track those things. So they tend to have a less number, but a number of browsers have many header fields, and also released version normally keep certain orders. So we call this one browser fingerprint. We can use that to tell this traffic is actually from a common browser. So this is a way to reduce false positive. Okay, so let's talk about the parameter. How do we do the feature engineering? So the challenge is obvious. It could be I read a paper. Some are doing a very small company doing a single gateway. They collect all the features, all the parameters. They have 6 million. Those are different parameters within 100 days. So you can imagine around the world, they are probably unlimited. These are features. So when we talk about features, we're talking about one pair of parameter name equal parameter of value. So this could be anything. User ID equal ABCD. So in order to do the effective machine learning, we need to figure out a way to reduce these dimensions. Otherwise, it's become impossible. But for example, if on device you try to convert a text of URL to a feature, you look at all the features collected. It's a computational disaster. Okay, the first method we thought naturally is we use the sorting method. So basically, we just count the hidden numbers. So these are parameter we happened like 10,000 times, and another one 5,000 times. We sorting it and pick up top 10. So with sorting, we can choose say how many malware samples have actually using these parameters. Okay, what's the problem with this sorting method? well, I put a cartoon here. Say, if you people only choose a popular flavor of chocolate, that's only a few. But how about the other? That's a long tail. So this long tail problem is if you choose the popular ones, you lose a lot of not unpopular features. Those unpopular even have a lower hit number. It doesn't mean it's not important. Probably it could be a significant feature to tell what is benign, what is malicious. Okay, the other method we use is using hashing method. So why we use hashing? Because when we look at, say, one URL or parameters, it normally doesn't have that many. We can say probably tens or maybe 100. So when you try to convert this string to your billions or dimensional feature space, it's very sparse. So to try to address this, we can actually use the hashing to convert those to compress the huge feature space to a fixed size. So, and even after that, it's still sparse. We don't have any issues with hashing collision. So we don't have, say, two different features hashed to the same bucket. For this fixed size, we can choose maybe we experiment with like 500, 1,000, 2,000. So we found the best number is around 3,000. So it's not that big, but it's still enough to avoid hashing collisions. So whether we address this number of dimension issues, we can try to extract some usable features from a pair of key value parameters. So if you simply just look at its text itself, the key equal value, it doesn't tell you much things. So I can give you an example. If you compare with apple and orange, not much to compare, but you add more features. Say apple, how about the shape? Apple and orange both round. Okay, they're similar. How about the taste? Both are good. So that's a similarity. How about color? Some are red, some are yellow. That's different. So we add more features to the object we want to study, these parameters. So these features we try to using a combination of its actual value and the type plus the length. So for example, if it's a number, we just call it a numeric. So if it's letters, pure letters, we call alphabet. If it's mixed, we call num alpha. We also have some kind of encodings, base 32, base 64. So it basically tell what type of this text is. Okay, now we are going to show you how we do this. We call it mapping of a parameter to a feature set. So here we show it's one parameter we're mapping to 4 features, 1 to 4. Say a user ID. So if you send a request, tell your CNC server, say you're from Black Hat 2017. The user ID equal Black Hat 2017. So the first feature we convert is just the original value itself. And second, we change the user ID, the key, to this type plus length. Then we keep the value as is. Then the third one, we use our key as is and change a value to the type and length. And the fourth one, we change both to the type and length. So we effectively change one parameter to 4 features. Then we do the hashing. So in the gray rectangle, long rectangle, it's our feature space. So when we hash, simply just hash the string, we got one bit in. So basically, that's the position among this, for example, 3,000 dimensional array. We got 1 bit. So for these parameters, we map the 4 features. We got 4 bits. So for if you have URL parameters have several URL have several parameters, then we got it's called it's a vector. It's one at a different location position. We have one bit. Okay, then how do we use this feature vector to do the comparison, say if adding kind of similarity, having commonality between. So I'll give you another example. Say if next year this malware evolved, they changed the user ID to Black Hat 2018. So we do the similar things. We got another 4 bit in the feature space. Now we compare this new malware with the last year's malware, then to see what the difference those parameters is. So we take this out and put 2017 back, and we'll overlap the two together. You can see, there's 2 bits have not changed. And there's another 2 bits have changed and become like occupied 4 positions. So if we choose a function to calculate the distance between these 2 feature vectors, so one simple way is we can just using count different bit and maybe divided by total bit. So in this case, the total bit is 8, and different bits, the 2 are same, so it did not contribute. So the other 4. You see, you don't see the mouse. The other 4 are actually contribute 4. So the difference is 4 and total is 8. The distance will be like 50%. You may say, okay, these 2 parameters looks quite similar, while the distance is like 50%. Okay, then since we can convert one parameter to 4 features, we can also convert to 6, to 10, whatever you want to do. So then you are based on your imagination, you can try to say, I want to focus on the key, because the key normally don't change. So we can add another mapping. So key equal nothing. So we add 1 bit for the key. So we can add a key equal type of value. So for the values, we only care about type. We don't care about length. So if they just change the length and keep the same type, that will be the one same bit. So from our experiments, we think we can do. We did 1 to 4, 1 to 6, 1 to 8. We found out like 1 to 6 is pretty good. Actually, we make our 4 out of 6 to be the key related, because from our observation, the key is normally don't change. But actually, from some malware samples, we see those attackers are very smart. They reverse, so they put our value as the key and key as the value. So but luckily, there's not many examples doing that, but it does break our scheme. Oh, okay. Okay. Now we have our feature vectors. So then we can do our machine learning. So it's very cool. There's a very good online course from Stanford. That's basically I learned from that. That's my first machine learning course. So I put that logo here. Then we need to figure out the way, because there's so many algorithms to do the machine learning. So basically, the 2 major types is supervised versus unsupervised. I will talk about what's the advantage and disadvantage of the 2 methods. Okay, supervised learning, I copied from Wikipedia and supervised, so I'm not going to read it. So I just say there's a lot of information out there. For our purpose, we compared on the left panel is unsupervised and right panel is supervised. We say for the unsupervised, we don't need a benign samples. We just need a positive black samples. For the supervised, we need both. Actually, we need a very good sample for the white, because otherwise you won't get a good model to tell. Because for the supervised method, it tries to find a difference. It tries to separate. It draw a line to separate 2 families. But for the unsupervised, they basically try to find the similarity. They found the common things and put them together. So, and also, as I talked, we are doing a product. So it's very important for we have customer. Once you say, oh, this is a false positive, we must have a way to immediately to rectify. We want to be able to modify the model. So it looks like the clustering, the unsupervised, have a very good way. We basically just are to move that cluster from your clusters. But for the supervised, you have a model. It's hard to manually modify that. Then you have to either relearn to add some kind of information that this is white, you relearn, or you can use some kind of whitelist. But a whitelist is not very effective because whitelist is based on the domain and the URL and parameters. So if your same parameter happens on the other domains, you're probably not able to bypass it. Okay, another machine learning method comparison is supervised. As I said, it is hard. You have to add new data and new labels and try to relearn the whole model. For the unsupervised, basically you can do the incremental. So you can just add your information. So for this diagram, so the first we do the 4 clusters. Then we add information that is good enough to have the cluster 5. But for the unsupervised, for the supervised, you basically have to relearn the things. So it's important that we do the high scalable, high performance method. So take time to relearn the whole millions of feature vectors. It's really hard. So the verdicts, we do a lot of comparisons. We use supervised machine learning. We use logistic regression. We found it's really good to do the binary classification. You can tell black and white very well. But for the multifamily, so we want to know the malware families. For the families, it's not that efficient. But the good thing is the model size is small. But for the random forest, we got a big model which work very well for multifamily classifications. That model is kind of too big to fit on our device because we want to learn offline and use on the device. So, and also another problem is our samples. We got our samples which is based on the malware sample running in the sandbox. So not all the network connection within that malware samples is actually malicious. So you have some kind of sandbox technology that will also include some maybe normal background connections. So once our sample have this inaccurate labels, it's hard to make very good models. So that's why we see why we just using unsupervised. Because for us, for the products, the worst thing is false positive. Because once you have like each day you have like more than 100 maybe of that false positive, and your user, your customer will turn the feature off. They don't want to take a look of all these things. So we want to be able to conservative. We try to our model can detect the real true positive. We don't really care much about the coverage, the recall. Okay, so unsupervised have all this kind of benefit is good for us. So our verdict, so we choose this clustering method. But I do not call it unsupervised because all this kind of data is actually have the label. We actually know even inaccurate, it belongs to some kind of malware family. So I will rather call it a semi-supervised clustering method. Okay, this is another 2 slides. Basically, just copy the information from Scikit. So it's kind of acknowledgement to Scikit. They have this wonderful open source package for. It's also my first machine learning. I learned from them. They have, and also for the cluster, they have done a fantastic job to compare different methods. So it's probably not readable, but I just say there's a huge amount of information outside. And this picture is very good because it shows how this clustering method works on this synthetic data. So based on what kind of task you want to achieve, so you probably want to choose the right method. So in this case, we want to be able to do something. The first, we don't want to try for example, the one method called k-mean. You have to tell it how many classes you want. Then you try and see what's the best number you can achieve. I don't want to try that. And I found since our sample is not that perfect, so we want to use some way to remove the noise. So I choose to use dB scan, which is a very good way to, it's a density based. It basically can do any arbitrary shape, and it has the capacity to remove the noise. It also allows us to set some parameters. So, okay, I talked a little bit more. Okay, let's talk about the clustering method we actually use. So first we are doing the family based. So we already have family. So all the family labeled data are put together. So that's the number of data is not that huge. So within a family, we do the clustering. So using these feature vectors we just talked before. For the clustering algorithm, I just talked a little bit, because first we want to define this is called distance function or cost functions, which have some meaning. One thing is, we know we try to look at parameter change. So we want to have some distance function we can tell how many bits have been changed. So then we decide to use there's several like city block method, Hamming distance, whatever, to do this calculation. We choose Bray-Curtis. It basically can show, say, if one value changed, that will basically, in our scheme, one feature map to 6. The distance will be like, distance will be, if you say 0 is the same, the 1 is totally different. The distance will be like 66.7%. So that is the threshold we use to tell if the two feature vectors are similar or not. Then we will also have this minimum number, which can help us to say if a feature happens just once, then it might not be a commonality. If it happens more than maybe twice or 3 times, then that's the pattern we want to use. So we can set a minimum number. That's the benefit of dB scan. Then after we cluster all the features, we just need to pick called centroid, which will be exemplar for that cluster. That is used to do the calculation to see if incoming URL is similar or not. So here is a diagram shows. So on the left side, we have this number of URLs, feature vectors. So they just one this bitmap within the feature space. Then we do our clustering. So in this case, the family A, we have two clusters, and one is noise. Then pick up a centroid. Then we effectively reduce this number of samples to 2. Okay, the next features is we try to do the cross family merge, which is the intuition is there's among the different malware families, there's a lot of modules actually shared commonality. They are kind of module reuse. There's some kind of on the underground market, they sell the source code. So hackers just take an easy job. They don't develop by their own. They just buy some source code and put it together, make some change. For example, last year, first we have a lucky ransom. Very quickly we see the different variants very quickly. So basically they look almost the same, only change a little bit. So cross-family merge, we can actually to reduce the redundancy and find some commonality between the different families. So the way we do is say we have family 1 have 2 clusters. Then we have another family which also have 2 clusters. And among them, there's two clusters belong to different family are very close, very similar. So we can just merge them because when we calculate the distance between the centroid, it's within the threshold. Say it's very close, then we can just merge them together and create a new artificial family. So the original family becomes smaller, and the merged family becomes the new one, which shows the commonality between these 2 families. The next one is try to, because our clustering, we don't use benign white data, but we do have these things within our clusters. So once we see, your cluster is similar to white samples, that will be false positive. So we use the benign sample to do the cleanup, the pruning. So basically, we have, say, this is the clusters. Then we have a collection of benign samples. Then we just apply the same method, same distance function, same threshold. Then we figure out what are white in the model and take them out. Then we get a model which will never tell you those white traffic are positive. Okay, another post-processing is we try to add categories. Do I have time? Okay. Category is important for us to know better. So we actually do the same thing. We have these labels. We just label our clusters. Those will tell you this is kind of is a CNC connection, or it's like some other things. So the last we show our results. Basically, we have started with 300,000 samples, and with 10,000 updates each week. We have roughly 400 malware family, but among the families, only about 1,500 have these HTTP connections. So we only study those. So okay, there's another thing I mentioned. So beyond the URL, we also look at post. Somehow in the post body, we see something similar to the key values as parameters. Those are also transfer information outside. So we also take care of those as the same as parameters. So this is the flow we use. Essentially, we have data pre-filtering. Pre-filtering just we use popular domains like OpenJS have popular top 10K, which basically filter out those URLs because otherwise it would be too much for us to process. We do the feature extraction, do the clustering, and do the validation of model using the in-house testing data to make sure this is very good models. Then we can apply models to the real traffic and tell you this connection is good or bad. So our result is pretty good. We have like achieved for the 9,000 clusters, we can achieve 84% detection rate on a total close to 1 million malicious URLs. We couldn't do 100% because some connections just look exactly very similar to the normal ones. We cannot tell the difference. The malware family coverage is not that good, but based on the information, HTTP has to be within that family. So we cover about like 90% of the 1,500 families which have these HTTP connections. So actually, in the field, we detect some unknown URL connections, which our vendor have not collected in the data yet, but we found this new one, just a slight malware parameter change. Okay, this is here is one example. I just show this detect time, domain name is exactly the same. In the bottom, we have this thing called nom URL, which is the URL from the cluster. Then the URI is the one we detected. So from I use the color highlight. It's different, but it's similar. So okay. So the next I will pass this to Jing. He will talk about
Yeah. Let back to this. We found that the purpose of this topic is from human eye, you can say that 2URL is very similar. It's the same attack or same biases. But if machine, they very difficult to find. So that's the whole purpose. And I think everybody knows the machine learning stuff and do some access. But if you do the research, you will find very different and very difficult. Like how just said about. So you need, based on your objects, you need to customize your feature side. For example, we do a lot of the things, and then you need to define your model. Also, you also need to define your model input the functionality something. And after your calculation, you need to do some merge, do some pruning, do some other stuff. That's the whole purpose is make your whole the result is lower the false positive and can be the product. But still, that's not enough. From our experience, right, the malicious URL is just one dimension, but in reality, right, for example, the data source with the sample we use is very hard. For example, there maybe so need to use sandbox to run to find the PCAP, but sometimes you cannot get also the label. For example, the family definition we know is most time is maybe not very accurate, and last thing is still maybe you need some wide sample to do some filter pruning. Yeah, that's also for the product or the good results you need the highly quality data. And back to malware side, of course, we know the HTTP is major things continuous, but still a lot of malware, so a lot of satellite malware didn't use HTTP. Even they use HTTP, we cannot get the clean URL data. They may use different methods to hack. Also, all we know, for example, Loki, the old transcript is encrypted, and you're supposed to encrypt. So all these things still, the malicious, so we use machine learning to detect malicious is good, but that's not enough for our campaign, for the journey, And the whole product may bring the false positive and the false negative. For our architecture, today we will not to the detail, but I just give the brief, The one thing, for example, like we just said for the URL, right? The way we can use, we not only use URL, we also use other head, like talk about, for example, the domain, for example, the URL path, and we combine together. Then you need to put the correlation method, right, to get the high quality. And last thing is from global domain. For example, in our experience, we find if maybe 20 or 100 hosts, they have same the URL the detention, probably that means your detention is wrong. It's false positive. But that's just for the one the object, right? But let's back to the architecture, right? This is our one simple architecture. We say, like I just said, we call the NG forward. It means not only intelligent, also the NG forward fully functionality. So we have in the lower, right? We have fully the defenders, multi-defender from IPS, sandbox, intelligent. And in the middle side is maybe it's a whole the correlation engine. They will get all input and got some output. One output is give the fully forensic visibility and also mitigation. That's just one system, but the whole system, in the global whole system, you can do this kind of thing in cloud. Something like you need the architecture change, or you get a better architecture. Just one just samples, I don't say too much. But one thing I like to say is we talk about the separate queue chain, right? For example, so in this picture we have 7 stage and we have CNC stage, something like that. But we need to do the correlation. What detailed correlation means, I just give the full step currently so we use, for example, we can do the correlation scoring for the secure stage, for the CNC stage. Also, you can, for one host, you can do the whole 7 stage correlation. Of course, you need your own model. And back to the global, so you can do the correlation for the whole host. And last things, the whole model should be updatable because for the different customer, for the different site, you may have different problem. Some false positive may be okay for other side. Yeah, something like that. So yeah, back to our conclusion. What I want to say is machine learning. This stuff we already talked about several years, and the behavior evidence. But when we do the fully research, even when we do the product, we find that's not easy. Yeah. So from currently, from today's topic, we can know one thing is URL is key thing, so we can use machine learning to detect unknown. Yeah. And the second thing is, yeah, for the detailed model, right, so you define your customized feature set, customer model. Yeah, that's the key thing to successfully the machine learning. Yeah. Okay. Yeah, about that's all. So I think we can still take the question.
So.
Okay. All right.
Okay.
Okay, good. Thank you. Yeah.